Rick Hartley is an industry veteran who has spent decades working on PCB design and signal integrity. He's a well-known presenter who's taught seminars at numerous conferences, including the IEEE EMC Symposium, PCB West, and IPC Apex Expo. Throughout his career, he's worked in sectors involving the design of computers, telecommunications, automotive systems, appliances, and aviation electronics for major companies in the United States and 12 other countries. Rick has also been a member of the editorial review board for Printed Circuit Design magazine, and he's written numerous technical papers and articles on design methods to control noise, electromagnetic interference, and signal integrity. Rick recently retired as the Senior Principal Engineer at L3 Avionics Systems to form his own enterprise through which he teaches and consults around the world. Ladies and gentlemen, please welcome Rick Hartley.
Thank you very, very much. You're way too kind. One of the things you're going to hear during the course of this week about Altium's tools is that the new tool allows you to tweak line length based on timing, not length, not millimeters or inches, but timing. And I've been telling people for years that's the right way to tune lines. The reason we tune lines to length is to make them the same time. And it's all about time, it's not about length. And I'm really happy to see that they've taken a lead on that, because that's something that's desperately needed. The introduction was way too kind. Thank you very much, Lawrence. You're a kind human being. Okay, anyway, enough of that. We're going to talk this morning for pretty much the next hour about things that differential pairs that I've discovered that a lot of engineers don't understand about differential pairs. Some of the stuff you may know well, some of you may know all of this, some of you may know little of it, but we'll see. I start every presentation I do with a statement about reading. When I graduated from college, and I'm sure many of you heard this same keynote address when you graduated, the guy who did our commencement address got up and he looked at this group of people, and as it turned out back then, it was all guys. I mean, women, there were no women in engineering in 1965. Anyway, just a bunch of geeks. Anyway, so we're all sitting there ready to graduate, and the commencement guy got up and he said, "Now the learning begins." And I thought, what? What do you mean, now the learning begins? What the hell have I been doing for the last 16 years? You know, I mean, come on, now the learning begins. But he was right. The first 2 or 3 years of my career, which was started 55 years ago, the first 2 or 3 years, I was able to get by on what I'd learned in college. But somewhere in the late 60s, I realized, there are things I just simply do not understand. And so I bought a book. And I've been buying books ever since. I now own over 120 books. I've spent over $20,000 US on educating myself. And I can tell you with clarity, it's been worth every penny of the money, because it's that, and you know, Lawrence said I'm a brilliant person. I don't mean to be rude, but I'm not sure I would agree with that. What I've done through my life is I've read a lot, and I've associated myself with brilliant people. People like Mike Creedon, Happy Holden, and Max and others, Carl sitting here. I've associated myself with Lee Ritchie and Todd Hubing and Dr. Bruce Archambault and Eric Bogatin, whom you saw in the video a minute ago. I mean, I've spent my life around sharp people, and it's allowed me to pick up a lot of knowledge. I'm going to impart a little of that today. Anyway, this slide says read books, not IC app notes. I don't mean to be rude. If there are any IC companies here, I don't want to offend you. But I ignore IC application notes as if they were the plague, because frankly, 95% of them or more are incorrect. I have a very close friend who was here last year and the year before by the name of Dan Beaker. Dan works for NXP Semiconductor, and he's an applications engineer. He writes app notes. And if you ask Dan, how are NXP's app notes? He will say to you, for God's sakes, don't ever use them. They're terrible. And he writes some of them. And if you ask him, Dan, why are they terrible? What he will tell you, I asked him once that very question. I said, Dan, why are NXP's app notes terrible? Don't the engineers understand circuit theory? And he said, well, of course they understand circuit theory. They're engineers. They can tell you anything you want to know about a circuit and how it functions from a voltage and current standpoint. What they don't understand is board design. They don't understand how to lay out circuit boards to make them noise-free. I can tell you with clarity, if you're having an EMI problem, it is the circuit board. It's not what's in the schematic, more than likely. It's the board layout. If you're having an interference problem, it is the board layout. It all comes down to circuit board design. That's where the rubber hits the road. The schematic is the description of the circuit. The rubber hits the road at the board level. Anyway, a quote from my friend Lee Ritchie. Circuit application notes produced by IC manufacturers should be assumed wrong until proven right. I first heard Lee make that statement about 25 years ago at PCB West. And I was sitting in a room of about 100 people, and I snickered. And Lee said, who did that? And I said, I did. He didn't know me then. And he said, what, do you disagree? And I said, no, I snickered because I thought I was the only person in the world who believed that. I'm glad to see there are two of us. And then we both laughed. But fortunately, there are a lot of people today who believe this. I would encourage you to educate yourself not through IC app notes. Food for thought. Differential pairs were first used to transmit signals between bays of equipment on factory floors and later in supercomputers. We started using them. I was in an industrial control equipment company in the late 60s and through the mid 70s for the first probably 11 years of my career. And we first used them because of what you see in this picture. This is a picture showing a single-ended driver driving a signal from one bay of equipment to the other. Back in those days, electronics, what you can put on an IC today, back then would have been in a 2.5 foot wide bay that was 6 feet tall and 3 feet deep, and it would have been filled with electronics to do what today we can do on one IC. But we would put these bays of equipment in factories and in various environments around the world, paper companies, plastics organizations, all sorts of things. And we first realized that we had a problem because we attached the internal ground of our circuitry to the cabinet itself. And the cabinet's framework was then attached to a large metal plate in the factory floors around the various parts of the world where we installed equipment. And what we discovered when we'd run a signal and its return, the ground, if you will, from one cabinet to another, there was a difference between the earth potential between those two cabinets if we ran more than 20, 30, 40 feet. Basically, if we ran more than about 10 meters, we found ourselves with a voltage difference. And that voltage difference would actually establish current in the ground line even when there was no signal. And of course, when there was signal, it would create an error in the reading of the signal. And there were times when we measured as much as 10, 15, or 20 volts difference between cabinets that ran hundreds of feet or 20, 40, 60 meters, those kinds of distances. And so we realized we had to do something about it. So we lifted the ground from the driver, and we changed it out for a differential driver. Basically, we were using op amps, by the way, and I'm sure some of you have heard the word op amp. We were using Philbrick op amps. Were in a package, you remember them, Happy. They were in a package about this big, and they were probably 12, 14 millimeters thick. I mean, they were huge. And all it was a single op amp with 2 inputs, an output, and a voltage and ground connection. 5 pins, and these things were massive in size. Anyway, we left the original amplifier that was driving the signal. We added a second one that was a gain of 1 inverting driver, and we took the signal, ran it through the inverter, so we ran the original signal and the inverted signal between the two cabinets, and the receiver at the far end was simply a differential input receiver, also an op-amp. We set it up in differential input mode to receive the signal. The advantage of this was it got rid of the ground loop problem that we were facing because of the voltage difference in earth ground, or in earth, I should call it. I don't like the word ground. So, and that really was what solved our problem. We thought we were geniuses. This was in like 1969 or 70. We thought we were absolute geniuses, and we applied for a patent. And the US Patent Office smiled and said, "Silly fools, this has been done." And we had no idea. We thought we were just coming up with something that was brilliant and that nobody else had ever figured out. People had been doing this since the 1920s. We just didn't know that. Anyway, this is how we solved the problem of ground loops. And to this day, one of the main reasons that differential pairs are used, whether it's between systems, whether it's between boards in a system, or whether it's to cross a circuit board, one of the reasons they're used is so that the circuit will ignore offsets in ground. That is one of the biggest reasons that people use them. Let's talk a little bit about that. Before we do, I want to there's a couple things that I want everyone in this room to understand, because it'll help you to understand how and why things work. These are things I talked about in the class I did yesterday. There's only a couple of slides, so those of you who were there yesterday, you can nod off for about 5 minutes and then come back to us in a short while. The frequency of a circuit is not driven by the clock. It really has nothing to do with the clock. The frequency of a circuit is determined by the rising and falling edge of the outputs. It's all about rate of change of energy with respect to time. Engineers refer to this as dV/dt, dI/dt. But it is all about the change in energy level in the circuit with respect to time. And that has nothing to do with clock frequency. So keep in mind, this is the frequency that we are most concerned about. When you're designing a circuit, one of the things you need to know is, what are the rise and fall times of my devices? And don't think it's going to be easy to find that, because the IC companies don't make it an easy number to come up with. We usually go to IBIS or SPICE models is where we find most of the data. Data sheets, why would they put it in the data sheet? That would be helpful. Why they wouldn't possibly want to do that. If there are any IC companies here and I'm insulting you, I'm sorry. Not really, but I'll pretend I am. Circuits are lumped, meaning we don't really care how we route them and basically they have non-critical behavior when you have a long rise time compared to propagation time. In other words, in a lumped element circuit, the energy in the transmission line rises almost like the water in a bathtub. And that's why it will never misbehave, because it develops its energy in the line in such a long period of time relative to propagation time that it's very challenging for anything to go wrong. Crosstalk doesn't occur, reflections don't occur, all the things we concern ourselves with don't happen. In contrast, a line is considered distributed and has critical length and critical behavior when the rise time is short compared to propagation time. When the energy can rise to its peak level and then come down the line as a wave, that's when we have to take care of the behavior of the circuit. And it really isn't about the clock, it's all about rise time. I've run into people in my career, probably the most ironic of all of them was in 2006 or 10, I don't remember which it was. I was doing a 2-day class in Australia. And a young gentleman came up to me at the morning break and he said, I work for an elevator controller company. And we clock at the incredibly high rate of 500 kilohertz. They clocked at 0.5 megahertz. He said, we've laid out our circuit boards the same way for as long as our company has been in existence. We've never, ever had problems. And suddenly, over the last few months, we're building circuit boards. Same board we've always built, same ICs that we've always put on them, and suddenly we're building boards that aren't working right, and we have to patch them with this and that and the other, Band-Aid them to get them to work. And when we finally did get them to work, they wouldn't pass EMI testing. And we've never failed EMI testing. We're failing radiated emissions at 250 to 300 megahertz, and we're clocking at 0.5 megahertz. How is this possible? And the answer is simple. They were ignoring rise and fall time. It isn't about the clock. It is about the rise and fall time. The ICs they were using went through a die shrink, and suddenly rise and fall time got faster, and boom, they were in trouble and didn't even see it coming. And I can't tell you, I've seen companies go out of business because they failed to recognize the real problem before it hit them in the face. So understand that going into a design. Know the rise time, design to the rise time, not to the clock. This is a table that shows, that I put together probably 20 years ago, that shows how long a line can be, a transmission line on a circuit board, based on rise time, before you have to pay attention to it. Notice there are inner and outer layer lines. Why would there be a difference between inner and outer layer lines? Because energy travels about 15% faster on outer layers, which is another of the problems that people have run into matching line length. If some of them are routed on the outer layer and some on the inner layer, then they're not the same time, even if they're exactly the same length. There are so many things that play into propagation delay. You really need to understand them before you willy-nilly match length. Anyway, enough of that. This shows basically what we're dealing with. Look at the bottom 3 numbers. This is typical of what devices in use today look like. Almost, and they aren't 10 or 100K ECL anymore. This is an old table. But what they are, they have rise times in the 0.3 to 0.7 nanosecond range. Almost all processors, FPGAs, memory devices, and so on have rise and fall times between 300 to 700 picoseconds. And that's what this table's telling you. And you can see that when traces are longer than 10 to 20, 25 millimeters, if you're not paying attention to them, you're asking the world to harm you, and it's going to oblige. Mother Nature is going to kick you square in the behind if you're not paying attention to these things. This is aside from differential pairs, but it also applies to differential pairs. This last 2 slides apply to everything we do. And just 1 or 2 more on a subject that's near and dear to my heart. Where does the energy travel in a circuit? I was first asked this about 16 years ago by a man whom I came to idolize by the name of Ralph Morrison. Ralph sadly passed away a couple of months ago. He was 94 years old. In the last year of his life, I talked about him last year in a keynote I did in San Diego. About a year ago, at age 93, he was becoming bored with life, so he started studying quantum physics. Let's just pick up some minor little subject and, kind of suck it up into our mind. But that was the kind of guy Ralph was. He taught me years ago, I used to think in terms of voltage and current. And I used to think that the energy in a circuit was in the voltage and current, but it's not. The energy in a circuit is in the fields. All of the energy in a circuit is in the electric and the magnetic fields. It is not in the voltage and current. Zero energy in the voltage and current. Where do the fields travel in a transmission line? The fields travel in the plastic of the circuit board. In other words, the energy in a circuit travels in the plastic. If you have a twisted wire pair, where's the energy? It's between the wires in the plastic of the insulation of the wire. It is not in the wire, it's in the insulation and the air around it. That's where all of the energy travels in all circuits, whether they're on a circuit board, whether they're wired, whatever they are. Energy travels in the space. As my friend Dan Beeker, who probably insulted some of your senses last year with his wonderful song, It's All About the Space, to the tune of Meghan Trainor's It's All About the Bass. He actually wrote a song that his daughter sings about that, just so he can irritate you into remembering that the most important thing you need to know is that when you route a trace, you better define the other side of that transmission line. Because if you don't, those fields are going to spread and they're going to leave you an unhappy individual. because all the energy is in the fields, and if they move position, they're going to couple energy into other things. That's why we have interference problems. That's why we have EMI. Forget voltage and current. Start thinking about the fields. This is a transmission line. A transmission line is any pair of conductors that move energy from point A to point B. The energy moves in the dielectric space. The voltage is across the copper features. The current is in the copper features. The fields travel in the dielectric space between the line and what I've shown here is I'm assuming a ground plane. I've shown it with a ground symbol, but that would normally be a ground plane. All the energy travels in the fields in the dielectric. When we pull energy out of a power bus, it's pulled through the dielectric space between the planes. Energy does not come from the power plane. Energy comes from the dielectric space between the power plane and ground. That's why it's so important in a circuit board, when you're setting up board stack, to have power and ground as a pair in the board. This silliness of putting in a 6-layer board power on 2 and ground on 5 with signals in between is one of the absolute worst mistakes you can make, because you're setting yourself up to couple power energy into signals and signal energy into the power bus. Because the energy is in the dielectric space. It's not in this power plane, it's in the space. And if you don't think about that when you're designing your circuit boards, oh Lord. Anyway, energy's in the fields. How we treat this return path really matters. So the question then, let's talk about differential pairs. The question then comes up, do the two lines of a differential pair constitute a transmission line? I just said a minute ago, any two conductors used to move energy from point A to point B define a transmission line. The answer to this question is sometimes yes and sometimes no. There are times when the two lines of a differential pair are in fact a transmission line, and there are times when they are two transmission lines. Let's talk about that. In its basic form, hear this carefully. In its basic form, a differential pair is two single-ended signals. It's not a differential pair. It's not some special thing that a lot of people think it is. And all the IC app notes I've ever read talk about the special qualities of differential pairs. You know what's special about differential pairs? They ignore ground offsets. There it is. That's the beauty of them. Beyond that, there really isn't much about them at all that's special, frankly. Yes, if you have them in a twisted wire pair, they will ignore common mode noise. Yes, there are other things they do. But on a circuit board, they don't behave the way they do in a twisted wire pair. The way they behave in a twisted wire pair is much different than how they behave on a board. Anyway, a differential pair is two single-ended signals containing equal amplitude and usually opposite polarity fields. The receiver is simply a crossing detector. It's looking for the two signals to be crossing somewhere in the linear region when the energy gets to the receiver. That's all it's expecting to see. And from that termination resistor at the end will initially have a plus-minus polarity, and when it sees a crossing event, it will flip to minus plus. And the next time an signal comes down, it'll flip back to plus minus, and so on. And that's all that happens at the receiver. It's a very simple operation. When transmitted in a twisted wire pair, this is a special case. And this is when differential pairs behave the best, when they're in a twisted wire pair. The pair the two lines of the pair do constitute a transmission line when they are a twisted wire pair. And have equal but opposite polarity signals in the two lines, unless they're LVDS, but you guys get the point. Have tightly contained electric and magnetic fields, and that's one of the better qualities of differential pairs. Because they're usually opposite polarity signals, they're like two strong magnets, where you put one north pole up and one north pole down, they're going to attract each other in a very tight fashion, and that's what differential lines in a twisted pair do. They have tightly controlled impedance. Ah, great, that's nice. We can terminate them properly and prevent reflections. The input of the receiver ignores unit-to-unit ground offsets because it doesn't have a ground reference. They reference each other, not ground. The input of the receiver has common mode rejection of noise. If I couple an AC signal, regardless of frequency, into that pair as it's traveling from this bay to that bay, any energy that's coupled into that pair when it gets to the receiver will be ignored because the receiver is a differential input amplifier that sends the voltage in the plus input on one side and the minus input on the other, and basically is subtracted from the signal. So in a twisted wire pair, differential pairs really do a lot of things that are special. So how does all this apply to a circuit board? Well, as I said a minute ago, it doesn't really. In a circuit board, you have two single-ended lines in two transmission lines. It's not a transmission line, it's two transmission lines that constitute two single-ended signals. That's all they are. It's as simple as that. And as long as you've got a ground reference underneath those two lines, there's nothing you can do to change that. They are two single-ended transmission lines, or two single-ended signals in two transmission lines. Most of the energy in the transmission lines is between the traces and the return plane below. I can't tell you how many people I've met who say, oh yeah, you got to keep that differential pair lined up perfectly to keep the coupling exactly. Most of the coupling isn't between the lines. 85 to 90% of the coupling from each of these lines is to the plane below. 85 to 90% of it is to the plane below. If there's a pair of planes on either side, then it'll be to that pair of planes, not to the other line. There is coupling between them, and how much coupling there is a function of how far apart they are. And a lot of people think, oh, they've got to be really close together because you want really tight coupling. It's irrelevant. Some of you who remember Lee Ritchie's talk probably remember him saying that he once routed a differential pair around the edges of a circuit board to prove to somebody that it doesn't really matter where they route. I did that too. I had an engineer who was so hell-bent on me having an absolute defined space between a differential pair and routing them in exactly the way he wrote out in lengthy description of exactly how that differential pair had to route or it wasn't going to work. So I routed it that way and I let him examine the board, and he said, it's what I wanted. I unrouted them, routed them around the edge of the board, we built a prototype and it worked perfectly. And that's when I told him the truth. And boy, was he hot. The point is, it's really irrelevant where they route. The only reason I route differential pairs together is so they will be about the same length. I mean, they do need to be about the same length because you do need for them to cross in the linear region of the rising and falling edges. And if they're not close to the same length, that's not going to happen. The differential impedance is defined by 2 times the odd mode impedance. Odd mode impedance is equal to characteristic impedance minus Z coupling. These fields that I showed initially between each line and ground, those are the fields that define the characteristic impedance of each line. Each line has its own impedance relative to ground. The fields that couple between them define what's called Z coupling. So when you take the characteristic impedance minus Z coupling, 2 times that gives you the differential impedance. Let me give you a quick example. If we have, hold on, sorry. If you have 2 lines that are 65 ohms each, and they're far enough apart, or close enough together, I mean, that you have 15 ohms of coupling between them, 65 minus 15 is 50, times 2 is a 100 ohm differential pair. If we lower the impedance, if we make them slightly wider and lower the impedance to 60 ohms, and move them far enough apart that they have 10 ohms of coupling between them, 60 minus 10 is 50, times 2 is 100. Both those scenarios are 100 ohm differential pairs. If we make them 55 ohms with 5 ohms of coupling, 55 minus 5 is 50, times 2 is 100. If we move them to where they have no coupling, which is what I did on that one board to illustrate to the engineer the importance of coupling, where they're 50 ohms with no coupling, they're still a 100 ohm differential pair, because they're two single-ended signals operating in the circuit board independently of one another. And whether or not they line up only matters if you're going to go through a non-grounded connector and how much they line up at the receiver. There does need to be some alignment between them at the receiver, which we will talk about in just a moment. And I've never seen an equation-based calculator that will give you an accurate impedance for differential pairs. I've found equation-based calculators that work for single-ended lines. I've never found one that works well for differential lines. So just, if anybody has one, please let me know. I'd love to know what it is. Because there are people out there who can't afford a $10,000 field solver or €9,000 field solver, and they'd like to be able to do this without spending the money. So for what it's worth, but I have never found one that works. There are advantages and disadvantages to tight or high Z coupling. Should traces be tightly coupled? Well, the reasons given for tight coupling are that the return current from one line is in the other. Well, we just proved that's not true. That's an absolutely untrue statement. The return current from one line is not in the other. The return current from each line is in the plane they reference, or planes they reference. It reduces unwanted coupling, crosstalk from other traces. Well, it will reduce unwanted coupling, but it doesn't eliminate it. The key to differential pairs, if we're going to couple crosstalk into them, we want to couple the same energy into each line, so the delta is 0. The difference in crosstalk between them needs to be as close to 0 as we can get. And we're going to talk about that in just a moment. Tight coupling does create different line widths. Yes. The advantage with tight coupling is you get a narrower line per given impedance, which makes it easier to design, easier to route, and so on. The disadvantage of tight coupling is it gives a narrower line per given impedance, which is harder to manufacture. And a lot of manufacturers, speaking of that, when you call a manufacturer and ask, what's the smallest, tightest, blah, blah, blah you can do, that's a mistake. The question you should be asking isn't what's the smallest line, smallest hole, tightest space that you can do. The question should be what's the smallest line, smallest hole, and so on that you can do without a cost adder. And the answer they give you is what should always be your target design. And you're going to find it's a whole lot bigger in most cases than what you're currently doing. So on most parts of the board where you don't need the tight requirements of small lines, you shouldn't be routing them, except in cases where they're controlled impedance. Or maybe make the wider line the controlled impedance, and where you have to neck it down, don't worry about its impedance. As long as the impedance discontinuity you create in the line by necking it down is short, relative, in other words, if it's a lumped length, it's irrelevant. It's as if it's not there. And I've proven that 1,000,000 times to engineers who, that's not true. Yeah, it is. Oh, yeah, it is. Narrower line, I just said that. And there's another issue. Let's examine two differential pairs. Here's a differential pair that has a 0.1 millimeter wide line that is separated by 0.16 millimeters, and it's 0.15 millimeters above the plane. For those of you who don't speak metric, that's a 4 mil wide line separated by 6 mils, separated by 6.5 mils, 5 mils above a plane. Here's a pair that's 0.18 millimeters wide lines separated by 0.36 millimeters, also same height above the plane, 0.15 millimeters. Those are 7 mil lines at a 14 mil spacing. Both of these are 100 ohm differential pairs, both of them. Here's the eye diagrams of those two at 3 gigahertz. The upper one is infringing on the eye mask. In other words, it's at the point where it's at risk of creating signal integrity issues. The wider pair is not. It's quite a distance off the eye mask. And what's the difference between them? The answer is skin effect. Sometimes separating differential lines by a wider distance so you can make them wider makes sense. And that could be for manufacturing reasons, that could be for reasons of signal integrity, that could be for any number of reasons. Every app note I've ever read says, bring them really close together. It's not always the right thing to do. Please understand the importance of that. And there are other conditions where tight coupling isn't a good idea either. This is just one example. Manufacturability is another. Let's talk for 1 second about crosstalk. If I have the tightly coupled lines we talked about a minute ago, sandwiched between planes, and by having them between the planes, I will reduce interference from the outside world, and that's a good thing. Planes offer a 60 to 80 dB isolation factor because fields do not move through copper. High-frequency fields, both electric and magnetic fields, will not conduct through copper planes. They are shielded by those planes. So you partially shield yourself from outside interference by putting differential pairs between a set of planes like this. Going to that tightly coupled pair, the 0.1 millimeter wide lines, 0.15 millimeters above a plane, if I bring an aggressor, a single-ended line or another differential pair, it really is irrelevant, within H, 0.15 millimeters is H, that's height above the plane. If I bring that aggressor within H distance, the coupling into line B becomes 12%. The coupling into line A is 2%. Now, people tell me that by putting differential pairs, by tightly coupling them, it helps eliminate crosstalk. We just said a minute ago, the important thing about crosstalk is that the crosstalk into each line has to be as close to the same as possible. I wouldn't call 12% and 2% anywhere close to the same coupling. And I'm sure none of you would either. Sorry. So having them tightly coupled doesn't help lower crosstalk if other things are brought terribly close to them at all. And there's two messages here. One, that tight coupling doesn't lower crosstalk, at least not that much. And two, you can't route other things terribly close to differential pairs. Because what crosstalk will do is offset the crossing point. And that's exactly what you don't want to do with differential pairs, is offset the crossing point. Now, I tell you right now, it's going to be offset by some degree, and frankly, there's nothing you can do about it. All the length matching in the world is not going to cause those two lines to cross dead center at the receiver almost ever. It's almost never going to happen. You're going to get a crossing off center no matter what you do, and there's reasons for that, which we'll talk about. Let's look at the widely coupled pair that we looked at a moment ago, the ones that suffered less skin effect. What is the crosstalk with them? Well, the crosstalk into line B is 12% again. The crosstalk into line A is 1%. So did having tight coupling really make a difference? 12%, 2%, 12%, 1%? They're both terrible. Come on, these are horrible. These are not good crosstalk numbers. The only way you could get equal crosstalk into those two lines would be to put the aggressor above, on the next layer up, running in the same direction as the pair, right over the middle of it. I'm not suggesting you'd want to do that. I think that would be a foolhardy move. But if your goal is equal crosstalk, that's the only way you're going to get it. You won't get equal crosstalk into differential lines. I don't care how tightly you couple them. It won't happen. Yeah.
If you were to take that example of route half of your distance on one next to the B and then switch over and route the aggressor half the length on the A, wouldn't that do the same thing?
It would solve the problem, but that becomes, in my opinion, a routing nightmare. I'm not sure I'd want to do that because you would have to change layers and then bring them back up. And when you change layers with any signal, we're going to talk about the dangers of that in a minute too. So yes, it would. I don't know if you guys all heard the question. He said if you had them routing side by side and then swap them over with the aggressor running next to him, wouldn't that solve the problem? The answer is yes, but how do you cross them over without changing layers? And changing layers creates its own set of problems, which we'll talk about in a moment. Length matching requirements, which is designed to match propagation delay, propagation time. Primary consideration is to keep jitter to a minimum. What is jitter? Jitter is the movement in time of the data crossing point relative to the data path clock. In other words, the clock appears, you get a crossing event some X amount of time later. As long as that is consistent, cycle after cycle, it doesn't matter where the crossing point is. Ideally, we want to cross in the center of the two signals. That's the ideal scenario. But in reality, you see those hash marks? Those hash marks define the linear region of both of those signals. And the linear region is the center 60% of the rising and falling edge. Now, there are people who will tell you that the linear region is the center 80%, from the 10 to 90% region of the rising edge is the linear portion. The center 80% is what defines the rise time. The guaranteed linear region of a rising edge is only the center 60%. As long as those signals cross within that center 60%, you still will have no jitter. All three of these signals will produce zero jitter, provided they cross in the same exact point relative to the clock, cycle after cycle. Now, if you mismatch their lengths so badly that they start crossing outside of the linear region, then you will produce jitter, and that will produce bit errors. That will produce bit errors. If your concern is signal integrity, all you have to do is cross within the linear region of the rising and falling edges. In other words, make them close enough in length that they cross somewhere in the linear region every single cycle. That's all that matters. Skew is set up by the 20 to 80% region, I just said that, of the rising and falling edge. And this just talks about how to calculate that quickly. Let's talk about some reasonable skew numbers. What are reasonable skew numbers? Well, there's a group of engineers in the Dakotas. I didn't know there were any engineers in the Dakotas. Isn't it too cold there? Yeah, it's pretty cold. Anyway, there's a group of engineers in the Dakotas that are the engineering branch of John Deere tractor. And you're probably thinking to yourself, wait a minute, engineers for a tractor? I mean, how complicated is this? The latest John Deere tractor costs $1 million. If you're piloting the thing, as they call it now, in the cockpit, it's not a seat, it's a cockpit now. The thing will calculate exactly how far apart seeds need to be and how deep they need to be based on the hardness of the earth, the moisture, and it senses all this as you're driving through the field. And it senses exactly where and how to plant everything to get maximum yield in 3 months or 6 months or whatever the case may be. If the tractor breaks down in the middle of the field, it has a cellular link that calls John Deere's computer in Illinois and talks to the computer, explains what's going on to the computer. The computer diagnoses the problem and sends the farmer an email and a text that says, tweak this or tighten that or do this or that, and the problem will be fixed. Sometimes it can fix it, but it solves all of its own problems. This is an unbelievable tractor. This isn't a tractor, this is a tractor. You know, I mean, this is a serious tractor. These guys from John Deere came to PCB West one year, and they had a list that's similar to what I'm going to show you here, that shows how much differently they routed differential lines and intentionally misrouted them. And they kept making one longer and longer and longer and longer until all of a sudden it failed. And this shows how long they had to make those lines to make them fail. At 100 megahertz clock rate, where, now there is a relationship between rising edge and clock, and I'm sure all the engineers in here know that. Typically, you're going to have about a 720 picosecond, the center 60% of that rising edge is going to be about 720 picoseconds long, because of the slope of the rising and falling edge. In other words, as long as those two cross cycle after cycle within that 720 picosecond region, you're fine. The amount of timing skew that creates for you is plus or minus 360 picoseconds. Think about that. 360 picoseconds, a third of a nanosecond roughly. Energy travels at about 6 inches per nanosecond, or in other words, about 150 millimeters per nanosecond in a circuit board. At 150 millimeters per nanosecond, if you've got a third of a nanosecond of available skew, that means you effectively have a third of 150 millimeters as available skew. And that's exactly what these guys found. This is the inner and outer layer skew that they had to create before the circuit failed. They had to mismatch those lines intentionally by anywhere from 55 to 70 millimeters before the thing failed. It isn't critical at lower frequencies at all. In fact, it isn't critical at higher frequencies. Let's bring up some other numbers. 250 megahertz, you have plus or minus 26 millimeters of skew. That's plus or minus from a given point. So your overall skew is actually twice that. In other words, the two lines need to be the same length at 250 megahertz within 50 millimeters. I'm sorry, what? Yes. Within 50 millimeters, plus or minus 25 millimeters. Even at 10 gigahertz, which is 10 gigabits, which is 5 gigahertz, you have plus or minus 1.5 millimeters of available skew. I have never in my life length matched the two lines of a differential pair, including at 10 gigahertz. Never. I just routed them side by side and made them approximately the same length, and every one of them has worked every single time. I'm not suggesting that you ignore length matching. I'm telling you it's not as critical as every app note on planet Earth leads you to believe that it is. It's not a critical factor. There are things in your life that are important, like referencing ground on the next layer of the board. That's important. But matching line length and differential pairs, come on. So what else can impact timing skew? Board materials. With some styles of fiberglass weave, the pitch can actually cause the two lines of a differential pair to sit on areas of vastly different isobar. It's the dielectric constant of the board material that determines the velocity of the signal. Velocity is the speed of light divided by the square root of epsilon sub r. And as epsilon sub r changes, velocity changes slightly. So as signals travel in the dielectric space across the circuit board, because they're traveling through the dielectric, through that plastic and fiberglass and epoxy, as they travel across the board, they speed up and slow down as they hit different isobars. And when the two lines are routing side by side, they almost never line up as they go across the board. They're constantly jockeying slightly in position. So all these guys who say, oh, I want them the same length so the cross coupling, oh, come on, really? The worst case is 1080 and 106 fiberglass. They have such a broad spacing between the fiberglass fabric that when you route one line over a space and the other line over a weave, you actually can have as much, sorry, as a 0.5 difference in E sub r between those two lines, which means that you will get as much as 5 millimeters of skew in 75 millimeters of routing. And your length matching them, why? Think about it. Now, that's dangerous. That much skew is going to cause a high-frequency circuit to fail. And the message there is don't use these glass styles with high-frequency circuits. Either rotate your board slightly in the panel so you can never route over the glass like this, or use there are special glasses now that have been flattened so it looks more like a ribbon and less like a rope. Instead of looking like you've woven ropes, it looks like you've woven ribbon. And there are glass styles that are designed to stop this problem, because this is a serious problem. This isn't a minor problem. This is a serious problem. And if you're dealing with stuff above 2 or 3 gigabits, you're going to run into trouble by using the wrong kind of glass. Talk to your fabricator about what they think is the best solution. But look at these other styles of glass shown here, 2116 and 7628. 7628 glass is the glass material that's used to build all 4-layer boards, and almost all 6-layer boards are made out of 7628 glass. Look how tightly woven that glass is. How could that possibly cause a problem? Well, from a signal integrity standpoint, it never will. I don't care how fast your signals are. From an EMI standpoint, it's a whole other matter. When you route across either of these glass styles, you're getting very subtle minor differences from millimeter to millimeter to millimeter as the energy is moving across that board. And what it does is it causes those line speeds to change slightly. They keep constantly jockeying for position based on the change in E sub r. And that's not going to cause a signal integrity problem, but what is the danger? I can tell you right now, when a signal reaches a receiver, if you have a single 100 ohm resistor at the receiver, and that crossing point is not absolute dead center, you will develop common mode current in one or the other differential line, and that dramatically raises the risk of EMI. So if there's any difference in the crossing point off of dead center at the receiver with a single 100 ohm resistor, what wants to happen is when you're not centered, one of the lines wants to go back to the reference, and there's no path to the reference voltage, whatever it is. And I'll tell you in a minute how to solve this problem. Because what I've just described is a condition where if you're terminating with a single 100 ohm resistor, you're almost guaranteed to have EMI no matter what you do. No matter how tightly you route your lines to make them the same length, no matter what you do, they will arrive at slightly different times. Great. And that's the reality of life. That's not the maybe of life, that's the reality of life. So, and I actually just told you everything that's on this slide. I've actually already gone through it. The solution to the problem, instead of using a single 100 ohm resistor termination, is to use two 50 ohm resistors and have their connection point go through a small value capacitor, 5, 10, 20 picofarads, to the reference voltage, whatever it is. If you're dealing with LVDS, for example, the reference voltage will be a voltage. And there are other types of differential pairs where the reference will be a true reference voltage. With most differential lines, where one goes high and the other goes low, that goes from negative to positive and positive to negative, the reference is going to be 0 volts. So in most differential pairs, you simply need to provide the energy at the end of the line through the 2 resistors and a capacitor to 0 volts, or to ground, if you want to call it that. And that will solve the EMI problem. Dr. Howard Johnson came up with this about 20 years ago. And he published a paper on it then, and I have a copy of the paper for anyone who's interested. Don't have it with me, but I have a copy of the paper at home and happy to send it to anybody. It's very important to understand that with all of the length matching in the world, you can't make them arrive at the same time because differences in materials will cause slight imbalances. And slight imbalances won't lead to signal integrity problems, as I just showed you from that table. I mean, my God, at 10 gigabits, if you've got plus or minus 1.5 millimeters of available skew before you're going to have a signal integrity problem, that's a ton of skew. I mean, that is a ton of skew. 1.5 millimeters. That's a lot. It's about EMI, and this is the solution to stop the problem. That's why when I route a differential pair, I just route it. I just route them. I put them together because I want to do the best I can to minimize crosstalk. And I keep other stuff away from them by 3 or 4 times height above the plane. I mentioned a short while ago when I showed you those crosstalk numbers, if you bring an aggressor within 1 times height above the plane spacing, there's nothing you can do to stop a crosstalk problem if they're that tightly coupled. You want to keep other things away by at least 2 or 3 times height above the plane. So I do that, I route them together, and I just route them. I never try to match length, I just route them. And if they're routed together, you're almost always going to have them within a given skew budget that will be satisfactory from a signal integrity standpoint. The other key issue then becomes EMI, and this is the solution to solve the EMI problem. Going back to single-ended signals for a minute, I talked about this in the session I did yesterday as well. One of the biggest causes of EMI is changing layers and causing the fields. Remember, when you're routing a signal, that picture there shows a signal line on layer 1 of a circuit board, a ground plane on layer 2, and a signal line traversing through a via to layer 3. The energy in that circuit when it's on layer 1 is in the dielectric space between layer 1 and layer 2. It's in the dielectric space between layer 1 and layer 2. If I change layers by going to the other, why do we change layers? To change direction. If I'm routing in the X on one layer and the next layer I route in the Y and the next layer the X and so on, then all I have to do is transition one layer to be able to change direction. And if I can do that in this fashion, the fields will couple in the space between the signal on 1 and the plane on 2. They'll couple through the hole in the plane. Remember, they won't travel through the plane, but they'll couple through the hole we've made for the via. And the fields will just continue on in the dielectric space between layers 2 and 3. And everything will work perfectly. You'll get no spreading of fields. What is the danger of spreading fields? Interference, potentially signal integrity issues, but almost always EMI problems. When you allow signals to change layers without controlling the fields, you run a high risk of causing EMI problems. From a signal integrity standpoint, you can change layers all day long and go anywhere you want on the board, and 95% of the circuits in the world from a signal integrity standpoint will care less. Where they will care is from an EMI standpoint. Because as the field spread, if there are other vias in that region, and the field is spread out by even a few millimeters, they're going to couple into other vias in the area. So now you're going to have the fields from these 2 or 3 vias all coupling together. And that's what ends up leading to EMI, because it creates common mode current in one or more of the lines, and that's where the danger comes. So this is an okay way to change layers. If you have to go from one ground plane to another, the best way to do it is to put a ground via next to it. This is a picture, again, from the ever-present Dr. Howard Johnson, showing what happens when you change layers with a ground via nearby. Now he's showing the current flow in the plane as opposed to showing the fields. And you can see that in this picture, the return current is on the top of the top ground plane with the signal on the top layer. When you go through the signal via to what would be the 4th layer in this board, the fields couple down through that hole and couple between the 2 vias, creating a return current in the ground via. And then the fields couple back together and go in the dielectric space between layers 3 and 4. Without the ground via, the fields will spread as far as they need to create enough capacitance between those two planes to allow a displacement current between layer 2 and layer 3. And sometimes, if those planes are far enough apart, such as in a 4-layer board, those fields are going to spread for 20, 30, 40 millimeters. How many other vias are going to be in that 20, 30, 40 millimeter area? A dozen, 2 dozen? And they're all spreading their fields, and all these fields are coupling together, and oh Lord, the EMI. It's unbelievable how bad it can get. People, most of the time, I spend most of my consulting time solving EMI problems because most of the engineers I meet have no clue about any of this. My job is so easy and I make such a ridiculous amount of money doing it. It's just unbelievable. I solve most EMI problems by simply adding return vias to boards or changing the positions of decoupling caps. I mean, the things are so simple and ridiculous, it's amazing. And if these guys would educate themselves, they wouldn't need to hire me. Anyway, the beauty of the fields going between those two vias, think about what's happening. Where's the return current? It's on the outside of the via barrels. There is no current inside of a via. Think about that. Oh, I've got to fill the vias. Do I have to use a conductive fill? You can fill it with peanut butter. It doesn't matter what you fill it with. Just if you have to fill it, fill it. Now, I wouldn't waste peanut butter on a circuit board, but you get the point. Anyway, it's very important to do this when you're transitioning from one ground to another. What about differential pairs? When a differential pair changes layers, do you need a return via? A lot of people will tell you, oh, it's a differential pair. They reference each other. You don't need no stinking return via. Oh, yeah? If you don't want the fields to spread just the way that these are two single-ended signals referencing the plane above or below. They are not some magical, mystical differential pair that do magical things because they're a differential pair. Without a return via, those fields are going to spread exactly the same way a single-ended signal will, because they are two single-ended signals. Please bear that in mind. When you change layers, if you have no return via or have an imbalanced return via, you will create common mode current in one or the other line. It will happen. Understand that. The best way to change layers with a differential pair is either with a pair of vias such as this, or you can put a single return via in this fashion. Any of those will work, but you have to take the fields through the dielectric from one dielectric layer to the next. You can't just ignore the fields, because when you do, you set yourself up for problems. Thank you very much. Any questions? Thank you. Appreciate your time.